Now I want to talk about the situation when there are potentially too many features. Recall when we introduced the least squares regression problem, we defined the input matrix as having n rows and d columns, where n, the number of rows, is much larger than d. But in practice, there are situations we might want to introduce many columns. For example, if we were using something like a bag of words embedding, where we're going to transform text into separate columns counting the number of occurrences of each word in the language, we could introduce many columns. For example, if we were to use a bag of words embedding where we introduce a column for each unique word in the language, then we might introduce many columns into our problem. And so in these cases, D could become larger than N. When D, number of columns, gets larger than N, the system of equations defined by the normal equations no longer is well defined. It's underdetermined. And just as before with redundant features, we introduce a potential computational challenge. Now, we can address these challenges by, again, using something like regularization, which we'll cover in future lectures. But it's worth understanding how things might go wrong when you introduce many features. Now, I want to show you how the introduction of many features can create a problem. And to do that, on this toy dataset, I'm going to introduce a class of features called a radial basis function feature. I'm going to use this class of features because it's pretty easy to create lots of feature functions, and I don't have to introduce a text toy dataset to demonstrate these problems. So radial basis function features, as I've defined in this function here, so these radial basis functions are essentially Gaussian bumps, or the PDF of a Gaussian, just like what we used in kernel density estimation. So this is the essentially part of the PDF of Gaussian here. It has two hyperparameters. These are parameters that we're going to have to determine in the design of the feature function that are not optimized as part of solving the loss minimization problem. And those hyperparameters are the location where the feature function is centered, and beta, which determines how spread the feature function is. So it has a property that as x gets close to the location, in fact, when x equals the location, this becomes the x of 0, which is 1. So the feature is its highest value when x is at the particular location. And as x moves away from that location, it decays. So maybe I'll illustrate it here. So here I've plotted 3 different radial basis functions centered at 0. So the location is set to 0 for all 3 of these, with different values of beta. So a small beta means that the function decays quickly. A large value of beta means that it decays slowly. This is corresponding to the variance of the Gaussian if we were to think of these as Gaussian PDFs. All right, so that's how we define a single radial basis function. And so now we can define a collection of radial basis functions, in fact, a feature function phi, which will map a single column x to multiple different columns centered at different locations using the default value of beta, which for this notebook, I've set beta's default value to be 0.1, which means it's going to decay quickly. And so these features are going to be pretty sensitive to their location. So I define this phi Rbf. And if I give it a set of locations, so I'll place a bump at -2, -1, 0, and 1. So I create 4 bumps. Then I can run this phi Rbf feature transformation with 4 bumps and my matrix X. So that should give me, it gives me 4 columns, one corresponding to each of the bumps. And then the value in this column is essentially X evaluated at the corresponding locations in the original X feature vector. So with this feature function, phi Rbf, I can now define a linear model. And this linear model will use phi Rbf. In fact, actually, I need to pass a lambda. So I'm going to take phi Rbf and define a feature function only takes x. And I'm going to bind the locations to the 4 bump locations that we defined above here. So now this is a feature function just in x. Go ahead and run that. And so this constructed a linear model, which I can now feed the original x and y matrices. I can fit, and I will get 4 parameters. So this is my theta hat for this RBF4 linear model, which has 4 features corresponding to each of the 4 radial basis functions at the 4 bump locations here. And as before, I can also get the loss. That's a much higher loss than we had seen before. So I believe the earlier loss that we were computing just in a simple linear model case was, I'm scrolling up, it was 1.7723. If we go down here, our loss is much higher now. So that wasn't necessarily a good fit. But let's take a look at what the resulting model predictions are. Now, because I'm no longer fitting a linear or fitting a line, it's still a linear model, but it's in a linear model in a higher dimensional space. Because I'm no longer fitting something that's a line, I'm actually going to want to evaluate my model at more points on the x-axis so we can see the curves. So I'm going to take this lin space function in NumPy, which is going to generate, let's make it 500 numbers between, go down to memory, make it 200 locations between x min and x max, -1 and +1, so we get a line that goes beyond the data. All right, so this is my locations. We're going to evaluate this new model I just constructed. Let me walk you through this plotting code. So I'm going to create a figure using just the scatter data, the scatter plot for the raw data. And then I'm going to add into that figure the line that we constructed earlier. I will go ahead and evaluate that line at all of these new x test points. So I'm going to get the line that extends beyond the data so that it will line up with the other models that we construct throughout the rest of this notebook. So the x values for that line are going to be from x test. Now, just so you know, x test, just like x, is a column matrix. And so the plotting code won't like that. So I need to flatten it. I guess I should have left that there. X test.flatten just wants an array. So it'll flatten that matrix back into an array. And then model line was the model we trained earlier or fit earlier. I can now make it predict at all of these new x test locations. That'll give me a y hat for each of those locations. And again, I will flatten that. And then I've requested this scatter plot just draw lines. I could do lines plus markers, but I don't need to see the markers. So I'm just going to draw lines. And I've specified the plot, the name that will go on the legend to be the LaTeX code of y equals mx plus b. That's our basic line. And then I'm going to add that to the figure. All right, now I also want to plot the Rbf model that we just constructed. So again, I'm going to take x and set it to be the x test. This time I'm going to make y the model Rbf that we just constructed dot predict, again at the test locations and flattening, and I'll give it a name and so on. Finally, I want to plot each of the Rbf bumps that we constructed earlier, so you get an idea of what they look like. And again, I'm going to take the x test locations and evaluate my Rbf feature at each of those locations for each of the bumps. So actually, I'll set location to be one of the 4 bump values, and I'm going to evaluate the feature value at all locations across the x-axis, or at 200 distinct locations across the x-axis. All right, and this will show my figure. So run that, and there we go. So this is a plot. Here's our original y equals mx plus b line. These are each of the bumps in my new feature representation. So there are 4 feature functions, 4 columns, and they have a coefficient for the weight for that bump. So this probably has a negative coefficient, so a negative greater than or negative less than -1. So it's the bump was actually made larger and negative. This bump probably has a very small coefficient, and then this bump here has a fairly large coefficient so that it can go up and reach this point here. And likewise, this bump also has a pretty large coefficient, raising it up to here. So this is a linear model. This curvy thing is a linear model in a higher dimensional space, a linear model in those Rbf features. All right, now it's not a great fit. And as you notice, as you go far away on the x-axis, it has to go back to 0 because the Rbf feature values are all 0 far away from the locations. So this line will go off to 0 this way, and it stays at 0 this way as well. All right, so not a terrible fit, not a great fit compared even to our line. And now the question is, could we do better? And so the next thing I'll actually do is we can combine both of these feature functions. So let's do that. So the way we'll do this is we're going to take the feature function for the line and combine it with the feature function for the RBF at a particular set of locations. And we can define this new phi line RBF feature function. So let's run that. And so now if I give it X and the 4 bump locations, how many columns will it have? So if you guess 6 columns, you are correct. So there is the ones column that came from our line model, the X value that came from our line model, or our line features, and then the 4 RBF bumps that we had before. All right, so now we can construct another model. We'll call this model line RBF4, which uses this new phi line RBF feature function we just created. Again, we have to put this in a lambda because the linear model wants a feature function in only one variable x, and so we need to bind this 4 bump locations hyperparameter, the locations hyperparameter, in this lambda. So now we've constructed the model, we can fit that model, and as you might have guessed, hopefully, there are now 6 parameters in our model. So that's the intercept, the slope, and then the parameters for each of the RBF bumps, or the RBF features. And now we can evaluate the loss of this model. And this is actually a little bit lower. It was 1.7 something before, now it is 1.62. So this is actually better than even our simple linear model that we had earlier. So let's evaluate this feature function. Now, as before, we actually computed all the other plots, so we just need to construct one more plot, which is just the plot for the model line for RBF, evaluated each of these test points. So there's our plot. Very good. And so this line here, which I believe is purple, this purple line now is able to actually both follow this linear trend here, but also kind of weave between each of these points. And so that gives us a slightly better fit. So again, these are still linear models, but using an additional set of features. So now we are up to 6 features and we have 9 data points. So let's go a bit more to the extreme. Let's suppose we pick 20 bump locations evenly spaced between -3 and 3. All right, so we can run our phi line RBF now with these 20 bump locations. And it's going to give us 9 rows by 22 columns. So this is a matrix where D is in fact much larger than N. We can still proceed to define our linear model. Let's break this up into 2 lines. Don't read ahead. All right, so we can define our linear model and we can fit it. And it's actually going to work, which is a little bit frustrating. I say it works. It ran. We get coefficients, some of which are pretty crazy, like -9 times 10 to the 16, or -8 times 10 to the 11. So these are pretty large values, or -1.7 times 10 to the 5. So some really large coefficients. Now, that worked, but should it have, is a question I ask here. And there, I guess you should hopefully already be keying into the intuition why it maybe shouldn't have worked. Well, it probably shouldn't have worked because we only had 9 data points and we built a 22-dimensional model. It's 22 dimensions because we have 20 radial basis functions plus the 2 the simple linear model dimensions, the intercept and the slope. So it's 22 parameters we're trying to fit using just 9 data points. So that already seems like an underdetermined problem. We want more data to try to estimate that many parameters. The other way to look at it is that when we're going to solve this system of linear equations, when we're trying to solve the phi transpose phi times this theta variable, we're going to solve for theta equals phi transpose y. Right, to solve this, we'll need to invert this phi transpose phi matrix. And so this phi transpose phi matrix shouldn't be more than rank 9. It is going to be a 22 by 22 matrix. We can actually construct it here. This is our 22 by 22 matrix A. So that is the phi transpose phi. And if we ask NumPy to compute the rank, we see that the rank of this matrix is 9 because there were only 9 rows in the original phi matrix. And indeed, if we go ahead and use NumPy to try to solve for the inverse of this matrix, it'll also perform poorly. So we take the inverse of A times the A, we'd expect this to be the identity matrix. And this is very far from the identity matrix here. Change the output. So we'd expect this to be identity, and we're getting values that are, well, let's see if I can find some large values. So we'd like this to be 1. This is definitely not 1. These should all be close to 0. They are not. And in fact, we have some pretty large values here. So this is an off-diagonal value that's very large. So that should be 0. Or here, another large off-diagonal value. Right. So this didn't quite work for inversion. Just as a point of comparison, we took the phi from our earlier Rbf model, which is Rbf4. So this is a much more constrained. And so this problem doesn't have too many features. And so here, when we take the inverse of that B matrix, so phi transpose phi, we see that this is much closer to an identity matrix when we take the inverse times itself. Now we can still use this model to make predictions. So here we'll go ahead and actually render the predictions from this model. And we're able to do that because the solution that was constructed by calling the solve function still attempts to solve the problem. And so we do get parameters that are in some sense viable. And so we've actually applied the model here, and we can see that it does in fact seem to go through all the data points. And it does correspond to many of these bumps. But we have some very large, very negative bumps and some very positive bumps, and presumably a very negative bump here that goes out to cause this line to dip so quickly. All right, so that is an example of what happens when we add too many dimensions. It is interesting to note that as we added many dimensions, we started to adequately fit, or in some sense overfit, our data. And that's actually what we'll talk about in the next video. But I just want to give a quick overview of what could happen if you introduce too many features and the implications on solving the normal equations. Now, as noted earlier, the introduction of regularization will help address this. And in fact, regularization techniques will be critical when we start to deal with really high dimensional data. And it is not uncommon to actually have to solve regression problems where we have 9 or 10 examples and tens of thousands of dimensions. And this often shows up in genomics applications. So when we get to regularization, which we've not yet covered, this will help address some of the issues here.